Have you ever, like, looked at an aluminum can and thought about how thin that metal actually is? Like, you'd think it would just crumple under pressure, but it's surprisingly strong, you know?
It really is.
And it kind of gets to what we are going to be diving deep on today. It's all about the strength of metals. And we've got a really cool chapter from a material science textbook.
Yeah.
And it all starts with kind of a mystery.
Yeah, it is intriguing how, based on what we know about atomic bonds, we can calculate this theoretical strength of metals, but then, like, in the real world, they are significantly weaker.
Right.
And so that tells us that there's something else going on at, like, this super, super tiny level that's kind of influencing how these metals actually behave.
Yeah, so that's where these things called dislocations come in, right? They're like tiny flaws in the otherwise, like, perfectly ordered structure of metal crystals.
Exactly. It's kind of like, imagine you have this perfectly stacked pile of oranges, and you try to just, like, shove an extra one in there, like, halfway through the stack. And you can imagine that that would disrupt the whole stack, right? And that shift in the arrangement is very similar to what a dislocation does within a metal's crystal lattice. It's like a line defect that weakens the overall structure.
Okay, so they're kind of like weak points in the metal's armor.
That's a good way to think about it.
Yeah.
Now, the most common type is something called an edge dislocation. So picture a single layer of atoms in this crystal structure. An edge dislocation is kind of like shoving in an extra half plane of atoms into that layer,
Okay.
creating a sort of step or like a bulge in the lattice.
So it's not just a missing atom or something like that. It's like a whole extra row crammed in there, kind of.
Exactly, yeah, creating a bump. And this bump, this dislocation, it makes it easier for atoms to slide past each other when there is a force applied. Like, think about if you are trying to move a heavy rug across the floor. It's much easier if you can create a ripple in the rug and push that ripple forward.
Oh, interesting. So the dislocation acts like that ripple. So it allows atoms to shift positions more easily.
Yeah.
Got it.
And so this movement of atoms, this is what we call plastic deformation, meaning it's like a permanent change in the shape of the metal. So like bending a paperclip, for example, that involves plastic deformation caused by the movement of dislocations.
Okay. So does this mean that the more dislocations a metal has, the easier it is to deform, and therefore the weaker it becomes?
Precisely. Now, here's where it gets even more interesting. When you deform a metal, you actually create more dislocations.
Oh, right.
So it's like the more you bend that paperclip, the more of these weak spots you're creating within the structure.
Oh, so it's kind of counterintuitive. Like the more you try to work with a metal, the weaker it's becoming in the long run.
Right, exactly. But here's like the really cool part. We can actually use this to our advantage. By controlling and manipulating these dislocations, we can actually strengthen metals.
Okay. Now we're getting to the good stuff. But how do you control something so tiny?
Well, there are some tricks we can use, and they all kind of revolve around the idea of making it harder for those dislocations to move. And one way to do this is to actually reduce the size of the grains within the metal.
Grains, like, are we talking about like grains of sand inside the metal?
Not quite sand, but you're on the right track. Metals are made up of these tiny crystals called grains,
Okay.
each with its own like unique orientation. And the boundaries between these grains act as obstacles for dislocations, making it harder for them to kind of move through the material.
So it's like setting up roadblocks for these dislocations.
Exactly. And the smaller the grains, the more roadblocks there are, the stronger the metal becomes. Think about forging, for example. When a blacksmith hammers a piece of metal, what they're doing is they're refining the grain structure, making it tougher and more resilient.
Wow, I never really thought of blacksmithing in terms of microscopic grains and dislocations.
Yeah, it's amazing how these like ancient techniques often have their roots in, these scientific principles. And speaking of science, another way to strengthen metals is through a process called solid solution strengthening.
Solid solution strengthening. What's the science behind that one?
Okay. So imagine, again, that you're trying to push that ripple in the rug. But this time, the rug is covered with little pebbles. Those pebbles would make it much harder to move the ripple, right?
Yeah, I see that. So those pebbles are like impurities in the metal.
That's a great analogy. Solid solution strengthening involves adding impurity atoms to the metal lattice. And these impurities can be smaller or larger than the host atoms. And they create these stress fields that essentially impede the movement of the dislocations. So again, it's kind of like adding those pebbles to the rug, making it harder for those ripples to move freely.
So we're essentially like adding obstacles to the dislocation highway, making their journey a little more difficult.
Precisely. And we see this in action all the time. For example, Adding a small amount of nickel to copper makes that resulting alloy much stronger. That's why copper-nickel alloys are often used in marine environments, where you need that strength and corrosion resistance.
Interesting. So it's like a strategic doping of the metal to enhance its properties.
Exactly. And there's actually one more technique we need to talk about, and this one is called strain hardening, also known as cold working.
Cold working. Does that involve giving the metal a chilly workout or something?
Not exactly. Cold working means deforming the metal at a relatively low temperature,
Hmm.
and this increases the density of the dislocations. Remember that traffic jam analogy?
Oh, yeah, yeah. The more cars you cram onto the highway, the slower everything moves.
Exactly. Cold working is kind of like deliberately creating a traffic jam of dislocations, making it harder for them to move and slip past each other.
Uh-huh.
And it's the reason why bending a paperclip repeatedly makes it harder and harder to bend further.
Oh, so we're basically pushing the metal to its limits, forcing those dislocations to tangle and get in each other's way.
That's a great way to put it. And it's a very effective way to strengthen metals. It's used in all sorts of manufacturing processes, from shaping sheet metal to drawing wires.
Wow, this is all so fascinating. We've gone from these tiny dislocations to blacksmithing to strengthening metals. It's really amazing how these seemingly simple concepts have such huge implications for engineering and material science.
It is, it is. And, we've only just scratched the surface. Now that we understand how to make metals stronger, we need to explore what happens when we want to kind of undo some of those strengthening effects. And that's where annealing comes in. And it's all about using heat to manipulate the metal's structure.
Okay, this sounds like a whole new chapter in our deep dive. I'm ready to explore what happens when we turn up the heat.
Excellent. Let's delve into the fascinating world of annealing and see how it affects those tiny but powerful dislocations within a metal. Annealing is kind of like, giving this work-hardened metal a nice spa treatment. Oh, okay.
So it involves heating the metal up to a specific temperature. And what this does is it allows those, tangled dislocations we've been talking about to relax and rearrange themselves. And this reduces some of that internal stress, and it can actually partially restore properties like electrical conductivity.
So we are basically giving those overworked dislocations a chance to unwind.
Precisely. And the effects of annealing, they really depend on the temperature and how long you heat that metal.
Okay.
So at lower temperatures, you get something called recovery. And during recovery, what happens is those dislocations rearrange themselves, they reduce their energy, relieving some of that internal stress, and the metal becomes a little bit softer and more ductile.
So recovery is kind of like the warm-up.
Right.
What happens if we really crank up the heat?
So at even higher temperatures, we enter into something called recrystallization.
And this is where things get really cool. What happens is brand new, unstressed grains start to form within the metal. And these new grains, they have very few dislocations, and they essentially grow until they've replaced all the old deformed grains. So it's kind of like hitting the reset button on the metal structure.
Wow, a complete makeover for the metal. So it's like recrystallization restores it back to a more pristine state.
Exactly. And it becomes softer, more ductile, and its properties essentially go back to like where they were before all that cold working we talked about.
So it really is a balancing act, it sounds like. We can strengthen a metal by manipulating those dislocations, but then we can kind of soften it again with heat.
It is, it is. And it really highlights like the incredible control that we have over the properties of metals. But there's actually like one more twist to this whole annealing story. If you keep heating that metal even further after recrystallization, those new grains that have formed, they can start to grow larger.
And we know that smaller grains means stronger material. So if the grains get too big during annealing, does that mean the metal could actually become weaker again?
Exactly. Yeah, excessive grain growth can be detrimental to a metal's strength. That's why it's so important to control that annealing process very precisely. Finding that sweet spot where you get the right balance of strength and ductility.
So we've been mainly focusing on edge dislocations. Are there other types of dislocations?
Yeah, so there are also these things called screw dislocations, which are a little bit more complicated to try and visualize, but imagine like a spiral staircase winding through the crystal lattice.
Okay.
A screw dislocation kind of creates that same sort of distortion, like a ramp that spirals around a central axis.
Gotcha. So instead of a bump or a step, it's more like a twist in the lattice.
Exactly, yeah. And screw dislocations can move, and they can contribute to plastic deformation, but edge dislocations are definitely more common, and usually they play like a bigger role in how a metal behaves.
Okay, cool. So it's those edge dislocations that are the real movers and shakers in the world of metals.
You could say that. Now, we've been talking about how metals deform under stress, and the textbook actually goes into some of the calculations that help us predict this behavior.
Calculations. Oh, I'm always up for a good equation or two.
Yeah.
So what are we calculating exactly?
Well, we can calculate something called resolved shear stress, which tells us how much of the applied force is actually contributing to the shearing action that makes those dislocations move. Remember, even if you are pulling on like a metal rod, there are actually these shear components acting on specific planes within that crystal.
Right. So we're trying to figure out how much of that pulling force is actually like pushing those dislocations around.
Precisely. And there's a specific value of shear stress. It's called the critical resolved shear stress.
Okay.
And this has to be reached in order for slip to occur. So think of it like as a threshold for plastic deformation.
So it's like the metal's resistance to letting those dislocations have their way.
Exactly. And once that critical resolved shear stress is exceeded, the metal starts to yield, meaning it undergoes permanent deformation.
Got it. Got it. So we apply a force, that resolved shear stress goes up, and if it reaches that critical value, bam, the dislocations start moving and the metal deforms.
That's the basic idea. Now, we've been talking about single crystals this whole time, but most metals we deal with in real life are polycrystalline.
Polycrystalline meaning they're made up of lots of different crystals all kind of mashed together.
Right, exactly. And those boundaries between the grains, they play a huge role in a metal strength. Like, imagine those dislocations trying to move through this kind of jumbled maze of different crystal orientations. It's not an easy task.
So those grain boundaries act kind of like a built-in obstacle course.
That's a great way to put it. And that's why polycrystalline metals are typically stronger than single crystals. The more boundaries there are, the harder it is for those dislocations to move and cause that deformation.
So it's all about creating a more complex structure within the metal.
Exactly. And the smaller those grains, the more boundaries you have, and
Yeah.
therefore the stronger the metal. And there's even an equation for this. It's called the Hall-Petch equation. It describes this relationship between the grain size and strength.
Wow, so there's a whole mathematical framework behind this.
There is. Now, apart from slip, which is the main way that metals deform, there's another mechanism called twinning. It's less common, but it can happen under certain conditions, especially in certain types of metals.
Twinning, so are we talking about like metal crystals that have identical twins?
Not quite identical, but imagine like a mirror plane that runs through the crystal lattice. Twinning occurs when the atoms on one side of that plane shift their positions to create like a mirror image of the atoms on the other side.
So it's like a section of the crystal just flips over to become a mirror image of itself.
That's the basic idea. And twinning doesn't contribute as much to the overall deformation as slip does, but it can have some interesting effects. It can sometimes even make the metal more susceptible to slip by reorienting that crystal structure.
Oh, so it's like twinning kind of sets the stage for more slip to happen.
Exactly. Now let's shift gears a little bit and talk about how we can actually use all of this knowledge about dislocations and strengthening mechanisms to actually engineer materials with like very specific properties. You know, it all comes down to controlling those dislocations.
Right. Restrict those dislocations and you get a stronger metal. But we've already talked about grain size reduction and solid solution strengthening. Are there any other tricks up our sleeve?
Well, there's one we haven't really discussed yet. It's called strain hardening or cold working. You know, we saw how bending a paper clip repeatedly makes it harder and harder to bend. Well, that's strain hardening at work.
Right. It's
Yeah.
like giving those dislocations a workout. But remind me again how this works at like the atomic level.
So when you deform a metal, you increase the density of those dislocations.
Right.
And as they get closer together, they start to actually repel each other, making it even harder for them to move. It's like, you know, a really crowded room. The more people you pack in, the less freedom of movement everyone has.
So it's like creating a dislocation mosh pit. The more they bump into each other, the less they can move around freely.
That's a great analogy. And that's why strain hardening is such a powerful technique for strengthening metals.
So we've got these three main tools for strengthening metals: grain size reduction, solid solution strengthening, and strain hardening. It's amazing how we can like manipulate something so incredibly tiny to have such a huge impact on the properties of a material.
Yeah, it is remarkable. Now, we've talked about how to make metals stronger, but there are also times when we might want to soften them or make them more ductile. And that's where those heat treatments come in.
Heat treatments like annealing.
Exactly. We can use heat to relieve that internal stress, restore ductility, and even change the grain structure of a metal. And the textbook actually goes into some detail about the different stages of annealing. We've got recovery, recrystallization, and grain growth.
Right. We've touched on those a little bit, but I'm definitely ready to dive a little deeper. What are the key things to know about these stages?
Well, recovery is like a gentle relaxation for the metal, as we said. It allows those dislocations to kind of rearrange themselves, release some stress. Recrystallization is a bit more dramatic. It's a transformation. Brand new grains form. It essentially resets the metal's structure. And then grain growth, as we talked about, involves those new grains getting bigger, which can sometimes be detrimental to strength.
Right. Okay,
Yeah.
so it's all about finding that balance, that sweet spot where you achieve the desired properties. It's fascinating how much control we really have over these materials. But we've been kind of focusing on metals in general. Are there any specific examples of how these principles actually apply to like real world materials?
Absolutely. Let's talk about steel. It's one of the most widely used metals in the world, and
Ah,
its properties are really heavily influenced by its microstructure,
right.
which in turn is controlled by those very same dislocations and grain boundaries we've been talking about.
Steel, the backbone of modern civilization. I'm eager to hear how this all plays out in such an important material.
Well, steel is essentially an alloy of iron and carbon, and the amount of carbon, along with the heat treatments that are applied, really determines the types of phases that form within that steel, which in turn dictates its properties.
So it's like we're adding another layer of complexity by alloying iron with carbon.
Precisely. And one of the most fascinating phases that can form in steel is called martensite.
Martensite. That sounds intense. What makes it so special?
Well, martensite forms when you cool a specific type of steel. It's called austenite very rapidly. And this rapid cooling, what it does is it traps carbon atoms within the iron lattice. And this creates a very, very hard and strong structure.
So it's like those carbon atoms are suddenly frozen in place and they create this really rigid framework within the steel.
That's a great way to think about it. And it's that trapped carbon, along with this very high density of dislocations, that gives martensite its incredible hardness. It's actually one of the hardest phases of steel. And it's used in applications where resistance and strength are super important.
So we're talking like cutting tools, blades, that kind of thing.
Exactly. Martensite is the key to those super sharp, durable edges. And it all comes back to controlling those microscopic structures, those dislocations, grain boundaries, even those trapped carbon atoms to achieve the desired properties.
It's mind-blowing how much is going on at this atomic level to influence the materials we use literally every day.
It really is. And this just scratches the surface of the really fascinating world of steel and its intricate microstructure.
Oh my gosh, I'm already feeling overwhelmed by the complexity.
hmm
But it's a good kind of overwhelm, the kind that makes you realize just how much there is to learn and discover. What else can you tell me about steel and its different phases?
Well, there are other phases besides martensite, each with its own unique properties and kind of formation mechanisms. For example, there's something called pearlite, which is what we call a lamellar structure consisting of alternating layers of ferrite and cementite.
Okay, you lost me a little bit there. Can you break those terms down for me?
Of course. So ferrite is essentially pure iron with a very small amount of dissolved carbon,
No.
while cementite is an iron carbide compound that has a much higher carbon content.
So perlite is like a layered cake of iron and carbon.
That's a very delicious analogy. And those layers, they form because of the way carbon diffuses and redistributes itself within the steel as it cools.
So it's like those carbon atoms are constantly on the move, finding their preferred spots within that iron lattice.
Exactly. And the rate of cooling, it determines how much time those carbon atoms have to actually diffuse and form these different phases. So slower cooling leads to these coarser structures, while rapid cooling gives you these finer structures.
So it's like we are choreographing this dance of atoms by controlling the cooling rate.
Yeah.
This is incredible.
Yeah.
Are there any other key phases we should know about?
Well, there's also bainite, which is another microstructure that forms at these intermediate cooling rates. It's got a kind of needle-like structure, and it offers a good balance of strength and toughness.
Okay, so we've got martensite, perlite, and bainite, each with its own unique structure and properties. It's like a whole family of steel microstructures, each with its own personality.
I love that. That's a great way to think about it. And, understanding how these microstructures form and how they actually influence the properties of steel, it's essential for engineering applications.
It's starting to feel like we're delving into metallurgy here, but I'm loving this journey into the heart of steel. What else can you tell me about how these different phases are kind of manipulated and controlled?
Well, we already talked about how heat treatments like annealing can soften steel and restore its ductility, but there are actually other heat treatments that are specifically designed to create certain microstructures.
Oh, intriguing. What kind of heat treatments?
Well, there's something called normalizing, and it involves heating the steel to a high temperature and then cooling it in air. And this refines the grain structure, creating a more uniform microstructure, leading to like improved strength and toughness.
So normalizing is like giving the steel a good balanced workout, refining its internal structure.
That's a great analogy. And then there's also something called process annealing, which is used to soften steel that's been cold worked. And it involves heating the steel to a lower temperature than normalizing and holding it there for a longer period. This allows for more stress relief and recovery.
So process annealing is like a gentle massage, easing those tensions and restoring its flexibility.
Exactly. And there are many other heat treatment processes, each with its own specific purpose and impact on the microstructure of the steel.
This is also fascinating. It's like we've uncovered this hidden world within this seemingly simple material.
It all comes back to those fundamental principles we talked about earlier, those dislocations, grain boundaries, and the diffusion of carbon atoms. By understanding how all those tiny players kind of interact, we can manipulate the properties of steel to create this huge range of materials for all sorts of different applications.
Wow, this deep dive has definitely given me a whole new appreciation for the complexity and the beauty of material science. It's amazing how something as, seemingly mundane as steel can hold so many secrets and possibilities.
It truly is a testament to the power of scientific inquiry and the endless wonders of the material world.
Wow, I feel like I've gained a whole new level of respect for steel. It's not just a simple metal, it's like this whole complex world of atoms and microstructures.
It really is. And we've only just begun to explore like the vast landscape of steel metallurgy. But before we get too carried away with steel, I kind of want to bring us back to this broader concept of dislocations and how they impact, material properties in general.
Okay, back to those tiny but mighty dislocations. What else can you tell me about them?
Well, so far we've mainly been focusing on how dislocations influence a metal's strength and ductility, right?
Right.
But they also play a huge role in other phenomena like fatigue and creep.
Fatigue and creep. Those sound a bit ominous. What exactly are those?
So fatigue is basically like the weakening of a material over time due to this repeated loading and unloading. Think of like bending a paperclip back and forth until it breaks. That's fatigue in action.
Okay, yeah. I've definitely experienced fatigue firsthand with a few paper clips in my day. But how do dislocations contribute to this?
Well, as those stresses are applied and removed repeatedly, dislocations can pile up and even form these tiny little cracks. And then those cracks can propagate and grow until the material eventually fails.
So it's like those dislocations are creating weak spots that just get more and more vulnerable over time.
Precisely. Now, creep is a bit different. It's the gradual deformation of a material under this constant stress, even at temperatures well below its melting point.
Oh, so it's like the material is slowly giving in to that pressure,
Yeah,
even if it's not being like actively deformed.
that's right. And dislocations play a role in creep as well. They can move and rearrange themselves even under that constant stress, and that leads to that gradual deformation.
So dislocations are involved in all sorts of material behavior, not just like, the straightforward bending and shaping we talked about.
Exactly. They're really these key players in the mechanical properties of materials, and understanding how they behave is crucial for designing and engineering, like everything from airplanes to bridges to even microchips.
Wow. It's incredible how much we can learn from these tiny little imperfections. They're like these hidden architects of the material world.
I love that. And it kind of brings us back to that aluminum can we started with. It might seem like a simple object, but its strength and its ability to hold up under pressure, it's all thanks to this really intricate interplay of dislocations and grain boundaries and all these other like microscopic phenomena.
This deep dive has really changed the way I look at these everyday objects. I'm starting to see these hidden worlds within everything around me now.
I think that's the real beauty of material science. It kind of reveals this intricate beauty and complexity that often goes unnoticed. And it really empowers us to understand and manipulate these materials to create the world we want to live in.
This has been such a fascinating and enlightening journey. We've gone from the theoretical strength of these perfect crystals to the real-world behavior of metals, with those tiny dislocations playing, a starring role throughout.
Absolutely. And we learned how to control those dislocations to make metal stronger, how to use heat treatments to soften them up, and how those same principles apply to more complex materials like steel.
I feel like I've gained this whole new appreciation for the power of material science and, the intricate dance of atoms that's constantly shaping the world around us.
I'm so glad to hear that. It's been a real pleasure delving into these concepts with you and, sharing the wonders of this kind of hidden world. I hope everyone listening has come away with a newfound appreciation for the beauty and, remarkable power of the materials that really shape our world.
I think they have. So, to everyone listening, the next time you see or hold a metal object, take a moment to just think about those invisible forces at play, those tiny dislocations and grain boundaries that are really holding the key to its strength, its flexibility, and its potential to transform the world around us. Until next time, keep exploring, keep questioning, and keep diving deep.